So another concept that we can address using the notion of the area under a function is average value. So many of you, of course, all of you know what an average is, but I want to give you a sort of different view of average that allows us to extend the concept just from a set of numbers to a function. So first of all, let's define the average value of a function on an interval as the signed area of the function on the interval divided by the length of the interval. So this is actually what the average value of a function is. Before we get to what that means for functions, let's just go over an example involving numbers, and I'll show you where we're going with this. So if I say find the average of these numbers, 1, 3, -2, and 7, what that means is that I'm going to add up 1, do this in a different color. Let's add up 1 plus 3 plus -2 plus 7 and divide it by the total number of numbers that I have. So that's going to be 4 minus 2 is 2 plus 7 is 9, so that's going to be 9 over 4. So that's the average of these numbers. But let's take a slightly different view of this. In other words, let's suppose that I plotted these numbers on a graph like this. So what I have here is what I have is a graph with where each number that I'm trying to average gets kind of a bar chart in the graph, gets kind of a piece of a bar chart in the graph. So the first one is going to be, the number 1 is just a rectangle of height 1 and width 1. The second number is a rectangle of height 3 and width 1. Now, all these rectangles are going to have a width of 1, and then the third rectangle is going to be a rectangle that's below the x-axis. So we count it as that's how we represent a negative number. So it's a rectangle of area 2, but it's below the x-axis. And the fourth rectangle, of course, is just the rectangle above the x-axis, again of width 1, and this time has height 7. So if I add up the signed area, if I write the signed area, is just going to be 1 plus 3 minus 2 plus 7. So that once again is 9. Now take a look at this at the length of the interval. Because I've assigned to each number a rectangle of width 1, that means the total width of all the rectangles is 4. So what I'm doing is I'm taking the signed area, taking the average value, is equal to the signed area divided by the length of the interval, and that equals, once again, 9 over 4. So we get the same thing, but we've now represented it graphically. So just to generalize this idea to the notion of functions, we can have a function like this. I've just drawn a very simple function, y equals f of x. We don't even have to know what it is. But what we would do is define the average value of f on the interval ab as being the signed area enclosed by f on the interval ab. And again, by signed area, I mean that for anything above the x-axis, we treat it as positive. For any area below the x-axis, we treat it as negative and just add them all up. And then we divide that by sorry, I wrote the word divided a little bit sloppily, but we divide that by the length of the interval, which is b minus a. So that would give us the average value of this function on the interval ab. Of course, we're not in a position yet to know the exact area, the exact signed area under this function, or enclosed by this function. We're going to get there. I know that some of you have already taken a calculus class and you may have an idea where this is going, but in this class we're not there yet. We don't have officially a way to find the exact area. We do, however, have a way to find the approximate area. So let's do this example. Let's estimate the average value of f of x equals sine x on the interval 0 to pi using an upper sum with n equals 8. So that means we want to do is take the interval from 0 to pi, which of course has length of pi, and divide it into 8 subintervals, each of which is going to have a length of pi over 8. And we're going to choose the highest point in the subinterval to represent the height of that subinterval. That will turn out not to be very difficult to do because we can see that the sine function, we know how the sine function works. It always bounces back and forth between -1 and +1, so on this interval it's actually always non-negative, and it reaches its peak at pi over 2. We know that sine of pi over 2 is 1, and it's going to be less for any other value in the interval. So that's going to give us, even though I've defined that we want to use an upper sum, meaning we want to choose the highest value of f in each subinterval, that's going to be easy to find as either the right or left endpoint because the function is increasing up to pi over 2 and decreasing for values beyond pi over 2. So we can use those rectangles there, and so let's just add up those rectangles. I'm just going to observe first that each rectangle has a width of pi over 8, and its height is just going to be the sine of whatever number we're using to stand in for the highest value. So we can see that it's going to be, we actually only need 1, 2, 3, 4, 5, 6, 7 of these because we use the pi over 2 twice. Pi over 2 is the highest value in both this interval and this interval, so that's why there are only 7 different values. But what we're doing is we're calculating the height of the first rectangle as sine of pi over 8, the second rectangle is sine of pi over 4, the third is sine of 3 pi over 8, etc. So now I'm just going to zip through the algebra here. Okay, so we see that the approximate area under the sine function on the interval 0 to pi using an upper sum with n equals 8 is given by 2.364. That's not the exact area under the sine function, but it is a good approximation of the area under the sine function. So now, in order to find the average value, we need to find the area under the sine function, which we only know its approximate value, and divide that by the length of the subinterval, which is pi. So that means that the average value, again, we only know it approximately, is going to be 2.364 divided by pi, which is approximately equal to 0.753. That's the average value, and I'll just mark here that the area is approximately equal to 2.36. Oops, write that a little neater. It's approximately equal to 2.364. Okay, so that's how you would solve an average value problem. And of course, later on in the course, we'll have a way to find the exact area, and then we can divide it by the length of the subinterval. But right now, we can only find the approximate area under a function.